All right, and we're back, everybody. Okay, so we're still, so we're still in this chapter about matrices, one of my favorite chapters. I think I've said that on Friday. This section is really fun too. This section is where we start to multiply with matrices. Multiply with matrices. Oh, don't look so excited, You're back first? I'm sorry. You need to lay down on the couch over there? On Friday we learned what a matrix was. We learned how to add, how to subtract, how to scalar multiply, but we didn't learn yet how we multiply two matrices together. Okay, that's what we're going to be looking at today. How do we multiply two matrices together? Okay, so the product of two or more matrices is called a matrix product. So that's where it's different from what was called a scalar product. Okay, a scalar product is when we multiply a number times a matrix. A matrix product is when we multiply two matrices together. All right, so again, the product of two or more matrices is the matrix product. The following rules apply when multiplying with matrices. All right, take a look at those two rules. Matrices A and B can be multiplied only if the number of columns in A equals the number of rows in B. Weird. The number of columns in A must match the number of rows in B. Okay. So if I have an M by N matrix times an N by P matrix, I'm just substituting letters in there for numbers because they could be arbitrary. If I have an M by N matrix and an N by P matrix, I can multiply those together because the number of columns in A matches the number of rows in B. Do we all see that? That's a kind of a really weird, unique thing there, where I only need the number of columns in A to match the number of rows in B. What does the number of rows in A and columns in B mean? Well, that means your product. They could be anything that you would want them to be. They could be arbitrary. These do not have to match. But where do they come into play? They come into play because that's your matrix product. The leftover dimensions turn into your matrix product. Okay? So let me show you some examples here. Okay, let me show you some examples. I can multiply those two matrices A and B on the left side. I can take A times B because I have 2 rows and 3 columns in A. I have 3 rows and 4 columns in B. Do you notice how the number of columns in A match the number of rows in B? The number of columns in A match the number of rows in B. That is what joins the two together. Okay, what does it become? What does the matrix product become? The matrix product becomes a 2x4 matrix. You take the leftover dimensions, the ones that didn't necessarily have to match, and that becomes your matrix product. Okay? So take a look here. We cannot multiply C times D because this is a 3-row 2-column matrix times a 3-row 5-column matrix. These cannot be multiplied because these numbers are not the same. I don't care that they have matching number of rows. That doesn't matter. Okay? I don't care about that. I only care about the fact that the number of columns in A has to match the number of rows in B. Okay? And the reason being is, look here. How many entries do I have in that row? I have 3 entries. It needs to match that same number here, 3 entries. I have 2 entries, but I have 3 entries here. That does not match. I cannot multiply them together. And you'll see how that ties in when we actually take a look and see how we multiply. This right now is just kind of prepping us to say, can we even multiply? So let's check some of those. Can we even multiply? Tell whether the product is defined. If it's not, if so, give its dimensions. Okay, so I've got a 3 by 4 times a 4 by 2. Can I multiply those together? Yes, I can. I can multiply those together. We'll put a little happy face down there. And then the resulting product is a 3 by 2. 3 by 2 matrix. Again, we have no idea how we multiply yet. This is just, can we multiply? Okay. I've got a 1 by 4 and a 3 by 4. Can I multiply those? No, I cannot. I cannot multiply those. A 1 by 4 times a 3 by 4. I don't care that the number of columns match in each one. That doesn't mean anything to me. The only thing that matters is the number of columns in A matching the number of rows in B, or in D in this case, C and D. So no, I cannot multiply those together. CD is undefined. Right? CD, there is no solution to CD. Does that make sense? Okay? That's just the rule to follow on if we can multiply. So, here we go. I am going to say, try to follow along as best you can with the wording down here, with this page. It will make more sense once we've done a couple of them. You'll be like, oh, that's what that means, okay? The reason being is when we define how to multiply, we have to make things arbitrary, or we have to make things in variable form because we don't really want to pin it down to be able to be anything. Like, for example, we have this matrix product. We're calling it P. P is the final matrix, and it's A times B. Whatever A is times whatever B is. Say that we can actually multiply. So that means the number of columns in A really does match the number of rows in B. Okay, we say that each element in the product, so in the final, notice how I use the term Pij, right? Lowercase p means in the final product. When we eventually multiply these two things together, it has some address Pij, where I and j are that's just the entry, that's just the address for that location within the matrix product. Okay, well, if we've got Pij, that means it's in row I, column j. The reason we're making it variables there is so that we make it arbitrary. It doesn't matter where it is. It's just some location in matrix product P. So say I have a location, Pij. It's the sum, every entry that has a specific address is the sum of the product of consecutive entries. Whoa, that's a big statement there. Sum of the product of consecutive entries. Okay, let's break that down. Sum of the product. Okay, that means I'm going to multiply things together, which makes sense. I'm doing multiplication. I'm going to multiply things together, and then I'm going to find the sum of those things. I'm going to eventually add them together. Okay, what am I multiplying together? I am multiplying consecutive entries. I am multiplying consecutive entries. Remember back here when I said these had to match? These have to match? What I mean by consecutive entries are these two, these two, these two. Right? I am multiplying those pieces together. Right? I am multiplying 3 and 2, then 5 and 9, then 7 and 0. And what am I doing to them at the end? I'm adding them all up. Okay? What do I do with that when I add it all up? Well, that's the entry Pij, wherever that is. Okay? So, again, Pij is the sum of the product of consecutive entries in row I in matrix A and column J out of matrix B. So you know how we didn't use the row and the column, right? That means you take the row out of the first and the column out of the second. The entire row out of the first and the entire column out of the second. That's where we're getting those two pieces. Okay? How do I know which row, which column? Well, it depends on which entry I'm looking at. Okay? Let me show you here. This is if I wanted to find what entry is that within the product? What entry is that? What's the address of that entry? Row 2, column 2, right? We would call that row 2, column 2, right? So that means we would take, think about how we say that, row 2, column 2. That means that we would take row 2 out of the first and column 2 out of the second. Row 2, column 2. That's the location right here, right? Row 2, column 2. So that means I would take row 2 out of the first and column 2 out of the second. Then I would multiply consecutive entries together. 3 times 6. So I'm getting that. Plus 4 times 8. Okay. When I figure that, okay, so 18 plus 6 times 8, what's 48? Or sorry, what's 4 times 8? 32? I would take 18 times 32, or sorry, 18 plus 32, so 50 in the end. I mean, I actually want to figure that out in the end. I want to actually go through it, do the sum and the product and all that. So know that it's just showing the work there. But you take row out of the first, column out of the second. Let's pick another entry. Let's say this one. Okay, now let's get rid of this guy. Okay, we're no longer talking about row 2, column 2. We're talking about row 2, column 1, right? This entry is called row 2, column 1. So I take row 2 out of the first, the same highlighted one I just did, and now I multiply it by column 1. Whatever. Those little highlights out of there. Row 2, column 1, because that's where this location is, right? Row 2, column 1. So I would multiply consecutive entries out of here now. I would say, okay, 3 times 5. Whoa. Yeah. 3 times 5 plus 4 times 7. 15, 28, add them together. Okay? That's the process. That's the process. Let's try it. Okay, flip it over on the back. This is what you guys have, right? WX 3, negative 2, 1, 0, 2, negative 1, 4, 7, negative 2, 5, 1, negative. Okay, perfect. My first year using these guided notes, so got to make sure that these are right on with my notes. All right, ladies and gentlemen, so let's multiply these together. First of all, I have to decide, can I even multiply? What are the dimensions of W? 3 by 2. 3 rows, 2 columns. Times X. Oops, sorry. 2 by 3. 2 row, 3 column. Can I multiply these together? Yes, I can. I can multiply them together. These match. So what is the resulting matrix product? What are the dimensions? What are the dimensions of the product? 3 by 3. So this becomes a 3 by 3. All right. So now we know we can indeed multiply them. Let's create our matrix product. All right, so I'm going to write a big blank three by 3. I'm going to show all the work here for this first one. All the work. All right. So I ask you, what's the address of this first location? This top left one? What's the address of that? Where's it at? 1, 1, right? Row 1, column 1. So what I'm going to do is I'm going to take row 1, multiply it by column 1. Okay. Row out of the first, column out of the second. And I'm going to multiply consecutive entries together. So I'm going to take 3 times 4 plus negative 2 times 5. Make sense? And you just keep on chugging. I like to kind of go across because now I'm gonna stay in the same row, right? This next one is gonna be row 1, column 2. So I don't have to move the highlight here. I say row 1, column 2. Now, this is location row 1, column 2. So I take 3 times 7, or 21, plus negative 2 times 1, negative 2. And then I keep it going. I say, okay, row 1, column 3. I take 3 times negative 2, negative 6. I take negative 2 times negative 1, positive 2. Is everybody following me there? Let's keep it rolling then. This is now no longer row 1. I've used up row 1. I've multiplied every row, every column in the second one by row 1. So let's jump down to row 2. And now let's multiply it with column 1. Okay, nice when there's a 0. 1 0 times 4, 5. 1 times 4 is 4. Plus 0 times, doesn't matter, 0. Okay, let's keep on chugging with that row. Row 2, column 2, that's the location here. 1 times 7 is 7, plus 0 times anything is 0. Let's finish off this row. Row 2, column 3. Negative 2 times 1 is negative 2, plus 0 times negative 1 is 0. Keep it moving. Row 3, column 1. Row 3, column 1. 2 times 2 times 4 is 8. Negative 1 times 5 is negative 5. Row 3, column 2. 2 times 7 is 14. Negative 1 times 1 is negative 1. Row 3, column 3. 2 times negative 2 is negative 4. Negative 1 times negative 1, positive 1. You follow me there? It's just kind of a long process. So let's figure it out. Let's actually add these things together. Find the sum of all of that. Okay, 12 plus negative 10 is 2. 21 plus a negative 2 is 19. Negative 6 plus 2 is a negative 4. 4 plus 0 is 4. 7 plus 0 is 7. Negative 2 plus 0 is negative 2. 8 plus negative 5 is 3. 14 plus negative 1 is 13. Negative 4 plus 1 is negative 3. And that's the resulting matrix product. Oh, no, that's fine. Questions about the process? Questions about the process? Okay, let's do it again then. Let me just duplicate you. Clone. Okay. Put it down because now we're going to do XW. Now we're going to do XW. Now, is XW going to be another 3 by 3? No. Can we even multiply? Let's check. X was again a 2 by 3. W is a 3 by 2. So XW is going to be a 2 by 3 times a 3 by 2. Can we multiply? Yes, we can. Those match. So the result is not a 3 by 3, but a 2 by 2. Oh, interesting. This is very interesting, people, because this is telling us that if we take X times W, is it the same thing as W times X? No. What? Commutative property doesn't exist? A times B is not the same thing as B times A? My whole life is a lie. What are you talking about? What? Yeah, that's the case with matrices. The commutative property does not hold for matrices with respect to multiplication. So we got to be careful there. WX is not the same thing as XW. All right, I digress. Let's keep going. Okay, here we go. XW is a 2 by 2. 1, 2, 3, 4 entries. Again, I'm going to show the work here. This is probably one of the last ones where I'll show all the work. I'll probably just jump to the answer in the end here after this problem. But let's take, okay, so this is row 1, column 1, row 1. Oh, sorry. I forgot. Now we're doing the other way around. Row 1, column 1. This is XW. And if you wanted to rewrite it backwards, because it might throw your eyes off a little bit there, that's fine. Okay, so what do we do with 3 entries? Well, the same thing we did with 2 entries. I take 4 times 3, 7 times 1, negative 2 times 2. And then I add it all together, all right? So 12, 7, negative 4. Everybody see what I did there? I just took 12, 7, negative 4. Okay, this is row 1, column 2. So I'm sticking with row 1 out of my first, and now I'm saying column 2. I'd love to have a 0. Love to see a 0. Negative 2 times 4, 0 times 7, negative 1 times negative 2, positive 2. Okay, row 2, column 1. Row 2, column 1. 3 times 5, 1 times 1, negative 1 times 2. Last one, row 2, column 2. Negative 2 times 5, 0 times, negative 1 times negative 1, positive 1. Okay, so the resulting 2 by 2 matrix is going to be 12 plus 7 is 19, plus a negative 4 is 15. Negative 8 plus 2 is negative 6. 15 plus 1 is 16, minus 2 is 14. Who is calling me right now? Potential spam. I love that they do that now. Potential spam's calling me. Negative 10 plus 1 is a negative 9. Ooh, that's fun. Questions about that one? Okay. Keep it rolling. What do you got next? Oh, yeah. We got to do a word problem with it. Yes, we have to. It's so much fun. The 2 stores held sales on their video and DVD sales with prices as shown. Use the sales data to determine how much money each store brought in from the sale on Saturday. Okay. Use a product matrix to find the sales of each store for each day. All right. Okay, so do we see here, how do we calculate, like if I wanted to calculate a certain income, I would take the initial price for the movie, price for the video. I love how this is still like VHS tapes, I guess. Price for the video times the amount of them that they sold. That will give me the amount that I earned for that particular thing. And then I would say, okay, $7.50 was the amount for the video, and I sold, 31 of them or so. I would take the price times the total sales, and that would give me my total income, right? So what I'm going to do here is I'm going to take this 2 by 2 matrix, and I am going to multiply it by 2 by 3 matrix. Now, can I even do that? Well, let's check. I've got a 2 by 2 times a 2 by 3. Can I multiply? Yes, I can. Now, take a look even further in. What was the label on this piece here? What was the label on the column out of matrix 1? What was the label on the columns? Videos and DVDs, right? The label on the columns here, it's row then column, right? The label on the columns is videos and DVDs. What was the label on the rows here? So it has to match to be able to multiply those things, right? not only do the amount of rows and columns of rows have to match, but also the labels, the meaning of those pieces must have to match as well. All right, so let's take a look here. Let's take this resulting 2 by 3, 2 row, 3 column matrix. Let's see what we got. Now I'm going to go into my calculator and I'm just going to run these numbers as I go. I'm not going to write it all out. Here's what I mean by that. I am going to highlight that. The highlighting is quite useful. Okay, this is, and it might also be useful just to make yourself like blanks so that you don't skip an entry. That always keeps me organized. All right, so this is row 1, column 1. Row 1, oops, I've been using yellow. I'm going to delete that one. Row 1, column 1. Okay, so I'm going to take 895 times 23 plus 1195 times 40. Everybody follow me there? 895 times 23, 1195 times 40. And that gets me 683.85. 683.85. Okay, this is row 1, column 2. Row 1, column 2. Okay, I can keep the 895 and the 1195. So now this becomes 895 times 31 plus 1195 times 48. 851.05. 851.05. Row 1, column 3. Okay, now this becomes, we get the same entry there. 895 times 25 plus 1195 times 42. 725.65. 725.65. Same process for the second row. Row 2. Whoa. Get back. Row 2. Column 1. Okay, we got 7.5 now times 23 plus 1250 times 40. 672.50. 672.50. Row 2, column 2. Row 2, column 2. Same thing. 7.5 times now 31 plus 12.5 times 48. 832.50. And then I take row 2, column 3. Row 2, column 3. All right, so now we jump up and say 25. 750 times 25 plus 1250 times 42. There we go. 712.50. 712.50. Now, what does this matrix product actually mean? Well, let's put back on our context. Let's reapply the context. Okay, well, what did we keep? We kept the rows out of matrix 1. So let's keep the row label out of matrix 1. So this is video world and star movies. Star movies. This is, okay, and then we kept the columns out of matrix B. Well, what were the columns? Friday, Saturday, Sunday. Friday, Saturday, Sunday. This tells us the exact amount of earnings for any day of the weekend for those two stores. So the initial problem asked, how much money did each store bring in on Saturday? Okay, Video World brought in $851.05. Star Movies brought in $832.50. Questions about that? Now, we could have done this one operation where we just saw what was happening on Saturday alone, right? We could have done that one operation alone, and it wouldn't have been that bad. But the nice thing about doing a matrix product like this is that we have all of the data and we're applying it to all, like we're applying the operation to all of the data. That way we have it when in the end we can kind of, interpret the data based off of what we see, so that we don't have to keep running different numbers and running different numbers. It's all done for us. And then we can say, okay, in the end, can I make any, observations about my final data? I applied all operations, and now let's see what's going on. All right, because every square matrix can be multiplied by themselves, we can actually take powers of any square matrix. Now, for example, what I mean by this is, if I had a 2 by 2 matrix, could I multiply it by another 2 by 2? Yeah, what would the result be? Another 2 by 2. So anytime you anytime you multiply a square matrix, what do I mean by square matrix? I mean a matrix that turns out to be the shape of a square, a 3 by 3, a 4 by 4, a 5 by 5, a 6 by 6, whatever. Whenever you multiply a square matrix by itself, the result is the same thing, right? If I took a 3 by 3 times another 3 by 3, what's the product? Another 3 by 3. Could I keep multiplying that back again by that same matrix, by that same initial matrix? Yeah, because it was originally a 3 by 3. Could I keep that process going forever and ever? Yes, and that process of repeated multiplication is taking a power of something. Okay, so let's take a look here. Let's find p to the third. Now, I caution you greatly, you do not, and someone will try to do this on their test and you'll miss a lot of points. You cannot, should not, don't even think about doing that. Right? I'm going to put a big X through that. You cannot just distribute that power. It does not work like that. I wish it did. That'd be a heck of a lot easier than what we're about to do. But you cannot just distribute the power like that. Okay? Because matrix products do not just multiply corresponding entries together. You can't do that. So what we have to do is actually take p squared. Now, what would p squared look like? Well, p squared would look like this. 4203, 4203. So the result would be another square matrix, another 2 by 2. Okay, well then this is a 2 by 2, so we've got to say, okay, let's get my highlighters out. Row 1, oops, let me do blue. Column 1. Get that yellow one up. Oh no. All right, so let's take a look at that. Row 1, column 1. Okay, well that would be row 1, column 1. 16 plus 0. 16. Okay. Row 1, column 2. 0 plus 0. Row 2, column 1. 8 and 6. 8 and 6. 14. Zero and 3. Oh, sorry, 0 and 9. Sorry, 0 and 9. 3 times 3. That's what was happening. So it looks very closely like I could just square it, but I can't. The only reason these numbers are coming out to, these top 3 over here are coming out to be ones that look like I should just square it, is because there was a 0 in my original, right? And zeros kind of cancel weird stuff out, so be careful with that. Okay, let's keep it going. I want to take p to the third, so I just multiply my original, p squared times, well, one more time. Okay, final matrix product is another 2 by 2. 1, 2, 3, 4. 1, 1. Okay, let's use the same highlightings. 1, 1. Okay, 16 times 4 is 64. 2 times 0 is 0, so 64. Row 1, column 2. 0 and 0, make another 0. Row 2, column 1. 14 times 4, 52? I better do that. 14 times 4. Oh, 56, good thing I did that. 56, plus 18. Plus 18. 74. And then I've got row 2, column 2. 0, 3 times 9, 27. So again, p to the third power is not like taking p and raising every entry to the third power. We just proved that. Questions about that? All right. And now again, we could do that to any power. Could I make it to the fourth power? Sure. Just keep multiplying it by p one more time. Can I make it to the fifth power? Sure. Just keep multiplying by p over and over and over again. All right. I'll stop talking now. That was fun. Fun day today, folks. Fun day.